Hi.
Hi, are you sure this course is just for 2499?
Yes, and you know this is the only course with this expertise across the world.
No way!
Yes way. Don't delay. Enroll now.
Geeks Learning.
Hi.
Hi, are you sure you can prepare for product based companies through this course?
Yes, sitting at home?
No way!
Yes way. Don't delay. Enroll now.
Geeks Learning together.
Yeah, hello. Very good evening to everyone present here. If I'm properly audible and visible, can you please write that in the chat box just for confirmation so that we can begin? Okay, hello Naikaj, how are you? Hello Simple Living with Aarti, how are you? So let us start then. Let me share my screen first and then we will continue. And meanwhile, let's give some time for other people to join as well. So you can find the link of the Google Jamboard session in the description of the streaming. And yeah, so my screen is shared. Okay, yeah. Thank you, Naikaj. Everything is perfect. Okay, so let us start then. We have 8 people with me right now. I would request each and every one of you to kindly write your name in the chat box to mark your presence. And I would also request to kindly interact with me during the session so that it will motivate me to deliver great content to you all. So we have a couple of announcements for today. So the first thing is that this is the first session of the tree series. So initially in the month of December, we concluded the graph series. We had a total of 12 sessions of graph in which we covered wide variety of concepts and topics and also did quite a lot of practice problems as well. You can access those in the GFG practice channel. Okay, so today will be the first session on tree, and in the month of January, we will be doing only tree. We will be coming live on every Monday and Tuesday at 10 p.m. Okay, and one more announcement is that from this week onwards, you will be also seeing a dynamic programming series on this channel itself. Okay, so one of my colleagues at Geeks4Geeks will be bringing the series to you all. So these series, including this graph, tree, and dynamic programming, are going to be very, very useful for your upcoming interview preparation for your internships and placements. Okay, so I hope everyone subscribes to this channel. Yeah, I would request everyone watching this with me right now, kindly like this streaming and subscribe to the channel because we have planned a lot of interesting content over the coming few weeks and months. Okay, so which are going to be very, very useful. Jay, I will be teaching primarily in C++. Okay, so I would request you to kindly follow the C++ language. Okay, and since C++ is the most popular language amongst all and majority of comfortable in that language, so that is the reason we chose C++. Okay, so in fact, you will be able to find Java solutions as well in the GFG portal itself. Okay, so no worries in that. So yeah, let me introduce about myself. My name is Gourav Kumar Shaw, and I'm presently in my third year at IIT Kharagpur, and I'm also a mentor at Geeks4Geeks. Okay, so let's start with the session then. Hello Tosif, hello Naikaj, hello Jay. Okay, I hope everyone is connected with me. So the first thing that we are going to study today is the definitions of binary tree, types of binary tree. We will also look into the various traversal techniques as well. So yeah, so have a look at, let's see. So basically what are binary trees? Binary tree are a kind of special type of, we can say a special type of data structure. We know about a variety of data structures like arrays, graphs, okay. So binary tree is a kind of a hierarchical data structure. Graph was also a hierarchical data structure. So basically we can represent data in the form of an hierarchy in binary trees. Hierarchy means at every level there is a certain amount of data associated with every level, and at every level the associated data behaves in certain in a special way. Okay, so for example, every binary tree consists of a root. Okay, so the top node, this is called the root of a binary tree, and every root will have two children. Since I'm calling it as a binary, it means that every root should have two children at max. So it can have one child also, it can have zero children as well, but at max it will have two children. This is called the right child and this will be called the left child. Okay, now see, as you can see, this left child has one child only, and this has another one child, this has another one child. So these children, these are called the children of a root of any node. Okay, now the node which doesn't have any children is called a leaf node. So the node at the end of the binary tree are called leaf nodes. Okay, now we have a few more definitions that are important from tree point of view. The first is the subtree. So what exactly is a subtree? So let us say you are standing at any given node. Let's say you are standing at this node. So whatever element of tree are present below this node will be your subtree. Okay. For example, you are standing at this node, then this entire portion will become your subtree. Okay. So this is a subtree for this node, and this is a subtree for this node. And let's say you're standing on the root. If you're standing on the root, then this entire tree structure will be your subtree other than the root. Okay, I hope you got the definition of subtree. So these are some of the few important definitions, and I'm sure, in fact, there will be many other terminologies related to tree as well. But these definitions will be enough for covering most of the concepts. And while we progress in the series, we will be learning about more terminologies. Okay. So now let us have a look into ancestors. So ancestors are basically the group of nodes. Just a minute. Yeah. So ancestors are basically all those nodes which are the ancestors of a given node. For example, you know the meaning of ancestors. So let's say your grandfather is your ancestor, your great grandfather is your ancestor. So let's say if I am considering this node, okay, so let's say I am considering this node. Okay, so this is the parent of this node is this node, and the parent of this node is this node, the parent of this node is this node, and the parent of this node is the root itself. So all the nodes which are parent of every other nodes are the ancestors. So I can say all these nodes are ancestors of the last leaf node. Okay, so given any node, all the nodes above that node till the very root, till the point of the root are the leaf node, are the ancestors. Okay, and there are no ancestors for the root node because everything is originating from the root node. So there are no ancestors for the root node. I hope everyone got it. Okay, another important point is that every tree, doesn't matter it is a binary tree or not a tree, if there are n nodes, then it should contain n minus 1 edges. Okay, so this is one of the important properties of tree. Okay, I hope everyone understood it. Any doubts still here? We discussed about the root, about the children, about the left child, right child, leaf nodes, and some other property of tree. And also we discussed about subtree and ancestors of a tree. Okay, any doubts here? So let's set a background here. Yeah. So we looked into the terminology. Now let us look into another important aspect of tree, that is there are various types of trees. Okay, I have listed down quite a few lot of names here, so which you can basically go through. So there is something called as full binary tree. Okay, so there is something called full binary tree, complete binary tree, perfect binary tree, balanced binary tree, degenerate binary tree. So let me tell you a definition of full binary tree. So a full binary tree is that tree in which every node has basically, let's say, either a zero number of child or two number of child. Okay, so let's say if this is one of the node of a binary tree, so this can either have two child or this can have no child at all. So either zero or two child. So this is called a full binary tree. And the definition of complete binary tree can be something like this. Let's say in a complete binary tree, what happens? All the levels are filled. Okay, so all the levels are filled except the last one. And in the last level, the tree should be filled from left to right fashion. Okay, so let's say all the levels are filled and this is the last level. Okay, so in the last level, something can be like this. Okay, so let's say this is a tree. Okay, yeah, so this can be a complete binary tree. You see the level number 0 is filled, level number 1 is filled, but the last level, it has to be filled from the left side. Okay, may or may not be completely filled, but if it is incomplete, it should only be filled from the left side. That is, if we start coming from the left side of the tree, I should get every nodes consecutively. All the leaf nodes should be present consecutively. So that is the definition of complete binary tree. Then there are other types of trees based upon various other conditions. So what you can do basically, yeah, so what you can do in this case is that you can Just Google search about various type of trees. Let me show it to you. Okay, so let's see about complete binary tree. Okay, so let's say I just googled this thing. Okay, so what you can do, there are excellent articles related to different types of trees present on Geeks for Geeks itself. So you can just open up this blog and you can just read that a complete binary tree is a special type of tree where all the levels are filled of a tree are filled completely except the lowest level nodes, which are filled from the left as possible, which this is exactly what I described just now. Okay, so any doubts here till now? Okay, hello Naikaj, are you there? Hello Tausif. So this is the part of a complete binary tree which we were telling about. So yeah, so also you can read about the various terminologies and definitions related to tree. Okay, so I hope many of you know about these. And in fact, if you do not know, no worries. You can just complete read from the Geeks for Geeks portal itself. Okay, so this is what it is. Okay, so any doubts still here? No doubt. Go ahead. Okay, Gaurav. Thank you. Okay, Naika, that's very well. Yeah. So these are the various types of trees. Let us now go back to traversal of tree. Okay, now yeah. Before we discuss traversal, let us discuss about representation of tree. Okay, so what exactly is representation? In fact, we just discussed that a tree is nothing but a data structure. It is a hierarchical data structure. Okay, so what happens in a hierarchical data structure is that you should have something to represent. So in fact, what happens is that, let's say array is a linear data structure. So we have something called way to declare an array. So how do we represent? How do we declare a hierarchical data structure? We do so in the by using the concept of structures. Okay, so what we do basically, a tree is represented in this fashion. We declare a struct called node, and in that node there will be two components. The first component will be the data itself, the value which we want to store in our data structure. Okay, so which will be represented by int data. This part is representing data. Second, second we have struct node. Okay, so since every node of a tree has to have maximum of two children, the left child and the right child. So we will be having two. We will be having two pointers from the data itself, from that node itself, which will be point to the left child of the tree, left child of the node, and the right child of the node. Okay, so it is something like this. Let's say if this is a representation of the tree, in that case we see that if this is a 1, okay, so this is represented something like this. So this is the structure. Now we see this each structure has three components. The first component is the data, in which I have stored the value 1. Now the remaining two components are nothing but pointer types. So this is pointing to the left part and this is pointing to the right part. Okay. Now we also, so I hope everyone got it till this point. So these are pointers. Okay. Okay, so now let us talk about node. So we will be declaring a new data structure called node in the form of int val. Okay, so this is basically a constructor inside the structure. So what is it is doing? It is helping us to create a new node. So whenever we want to create a new node, we will just call this constructor and supply it some value. So let's say I want to create a node called root node as 1. So I will call this constructor supply the value of 1. So it will create a node of value 1, and what it will do, it will point these both left pointer and right pointer to null. Okay, so this will help us to create one node. Okay, so this is how binary trees are represented in the form of a structures. Okay, so I hope everything is clear till here. Any doubts in the representation of binary trees? So you can read similar thing or similar very interesting article on Geeks for Geeks as well. Let me show it to you. In fact, you will also find problems on Geeks for Geeks portal itself. And meanwhile, what I want you all to do is basically there is a link for the uh, there is a link for Geeks self-paced course, so you can just check that course out. It's an extremely beneficial course if you're trying to learn about data structures and algorithms. And in fact, during my early days of preparing for data structures and algorithm, I bought that course initially myself as well. So that's very in that course, every concept is very lucidly explained. So it will be very very helpful for you all. Okay, so this was about that course. So yeah, so these are the various type of terminology that you should know. Let's see the coding part. You can see the coding as code aspect of it. Okay, so yeah, as I said, every it should be represented in the form of a struct. Okay, so this is how we will represent. And apart from that, yeah, someone was mentioning about Java in the course. Basically, in Geeks4Geeks portal, you will also see code written in Java as well. Okay, so no worries related to that. And apart from that, there are few definitions which I just skipped over, because as we progress over the series, we will get to know those definitions. So other definitions are maybe something like this. About binary search trees are there. Then there are other definitions like height of a tree, diameter of a tree. Okay, so that is one of the thing. We talked about siblings. Yeah, so if there are any two nodes which are basically of the same parent, then those two nodes are basically called siblings of each other. Okay, so that is, yeah, so that is one of the concepts that you should know about siblings of a binary tree. Yeah, so I guess these are enough content that we have just discussed. So let's move to the next part of our understanding. So next is basically about traversal techniques. So we know about two graphs, right? Two traversal techniques about graph traversal techniques. The one is the breadth first search, and the other is the depth first search. So basically, can we do a DFS and a BFS on a tree? Can anyone write that in the chat box? Okay, so like why, how, what is the use case of these traversal techniques, BFS and DFS, in tree? What will happen if I apply these traversal techniques on these trees? What will happen then? Can anyone tell me? You can see in the screen basically all the use cases about these. Okay, so let us see that in great detail then. Yeah. So what we can do here is that, let's say everyone knows about depth first search. So depth first search, let me give you a small brief introduction. So depth first search is basically a type of traversal algorithm in which we recursively go to the very depth of the tree. So let's, for example, if we are starting from the root node, then what will happen? We will go to the recursively call for every node, the right child and the left child. And when we are reaching the right child, it will again recursively call for its right and left child. So something like that happens until and unless we reach the leaf node. When we are at the leaf node, there are no child for further recursive decomposition. Then what will happen? The function will backtrack itself. So that is how we are basically going across the depth first search. It explores one depth, then again comes and explores the other depth. So this is one of the traversal techniques of a graph, and we will be applying this technique itself to write three different types of traversals in a tree. Okay, so why traversal? Because there are three different and the more very important traversal in a tree. The first is in order, the next is pre-order, and the third is post-order. All these three traversals can be written just by applying the concept of depth first search on a given tree. Okay, so basically, since the concept of the depth first search involves going to the very depth of a given tree, it means basically is that you are going to the depth of a given tree, and you are experiencing, and you are basically coming across various nodes. And let's say you keep track of the nodes. Okay, so basically, and if you just call the DFS function in a particular manner, you will get unique order in which you are visiting the node every time in the given tree. And those three different types are called in order, pre-order, and post order. Okay, so let us first talk about the in order traversal. So in order, pre-order and post-order are basically similar. All these three are basically similar type of implementation of the depth first search algorithm. Okay. So what happens in order is yeah. So what happens in order is that first the left node is written, after that the root is written, and then the right is written. Okay. So we will first go through the in order of this given example. So I have already written an example here. So let's say this is the root. The value of the root is 1. Then we have 2, 3, 4, 5, 6, and 7. Okay. So these are the left and right child. So what will be the in order traversal of this tree look like? Okay. So I have already written up the traversal techniques for in order, but how are we getting this? That is the idea. Okay, so as I just said that we have to apply the concept of DFS. Okay, so let us say that we start from our given root node, and then we will be traveling to the left part. Okay, then it means that we are coming to node number 2. Again, we will be traveling to the left part because we what a depth first search does is basically goes to the very depth of the given tree in whatever branches it is traversing. So then it will finally come back to 4. Now when it come back to 4, it doesn't have any other much more depth to explore. So in that case, what will do, it will just print out 4 because I want to print the left node first. After that it will backtrack itself, and then it will come back to 2. And when it will come back to 2, it sees that it is one of the root. So in that case, it will print the root because after left I am supposed to print the root. So if you consider this small subtree, this 2 is basically a root of the subtree, and then when it comes to the root, it will check for its right children, and it sees it is 5. Now again it will try to go to the depth of the 5, but in this case 5 is the last node. So what will happen, it will just print 5 now. So 4 to 5 got printed. After that it will go back to 1. Now it sees that 1 is a root of this entire tree, so it will print 1 because after left it should print root. So this entire thing becomes left part of the tree, this becomes the root, and this becomes the right part. Okay, so after it prints root, it will come and print the it will start exploring the right part. I hope everyone is following me. Yeah, so I hope everyone is following with me. What I just said is that first we explore all the left path, then we come back to root, and then we go to print its right path. So now when we come to the right path, so what will happen, we see that it is 3. The node number 3 is present, but node number 3 will also have a right path. But when we are coming to node number 3, we see node number 8 and node number 7. So node number 8 is the left path. So in order, we first go to its left path. So it will go to 8. Okay, so yeah, in fact this is 6, so it will go to 6, and then finally it sees that it doesn't have any other left or right. So what will happen, then it will just print 6 because left should be printed first. Then it will go back to its root, which is 3, and it will print 3, and after printing 3 it will go back to the right children, that is equal to 7. So finally it will print 7. So this is how the entire traversal of this tree look like in order fashion: 4 2 5 1 6 3 7. Okay, so this is the in-order traversal. Now if we talk about pre-order traversal, what will happen, we will print the value of the root first, and then we will go to the left part and then the right part. Okay, so I will show the dry run of pre-order traversal in the different slide. Yeah, so let me create a new slide here. Okay, yeah, so let us have a look at the pre-order traversal. So let me create a new tree. This is 4, this is 5, and let's say I put 6 here, and let's say I put 7 here. Okay, okay. Now according to the rules of pre-order traversal, according to the rules of pre-order traversal, we should have root first, then left, and then right. Okay, so first we should print the root, then the left part, and then the right part. Okay, so yeah, so this is a slightly different tree than the tree which I discussed for in order traversal, so that the dry run becomes very clear to you. So let me just explain pre-order in this fashion. So first we will print the root, so that is why we are printing 1. Then we go to this left part. Okay, so 2. Then when we come to its left part, it is also a root, so we print 2 again. Then we again go to its left part, we see 4. So now we print the value 4. Then again we come back to 2, we go to the right part, that is 5, and we print 5. Then we come back to 1 itself. After that we go back to 3 and print 3. Then we print 6, and finally we print 7. Excuse me for a while. Yeah, so this is okay. So let us just dry run the concept of pre-order in this example, which I just this is a modified version. Okay, so this is a different tree than my previous example. So first we have to go to the root. So we come across 1. So we print the value 1. Then we go to its left part. Left is 2. Now since 2 is also a root of a tree, it will print 2. Then it will go to the next left part, which is equal to 4. So it will print 4 now. Then again it will go to the left part, which is equal to 7. It will print 7 now. So now it will come back to 4. It sees that it doesn't have anything to its right. So it goes back to 2. It sees it has 5 to its right. So it prints 5. Now when on 5 it sees that it doesn't have anything to the right and left of 5. So it will come back to 2. It comes back to 1. It again come back goes to 3. It will print the value 3 here. Now again 3 will go to its left and sees 6. So it will print the value 6 here. And finally 6 also doesn't have anything back to it. So it will come back to 3, come back to 1, and finally the program is over. So this is the pre-order traversal of the given tree. Okay, so this is a dry run of the pre-order traversal. Now similarly we can do for the post-order traversal as well. So what exactly is post-order? We did in order, we did pre-order. Post-order is left, right, and root. Okay, so let us implement the post-order traversal. So is there any doubt still here? How am I dry running these? Lalit is asking if I'm Indian. Yes, Lalit, I am Indian. Okay, so we have 10 people with me right now, and I would request everyone to kindly like the streaming as well as subscribe to the YouTube channel as well. So yeah, yeah, and also as I just announced that this is a graph and tree series going on in the month of January. We will be having all the tree sessions, and apart from that, we will also be having a series related to dynamic programming in the month of January itself, which will start from, I guess, from Friday. Okay, so kindly have a look at that as well. Okay, so let us look into the concept of post-order traversal. Okay, so in post-order traversal, what it is, first you have to print left, then right, and then the root. So let's say we go to the left, 2, then again we go to left to 4, and then again we go to right, then that is equal to 4, that is equal to 7. So finally we are at node number 7. So after left is printed, we need to go back to its right. Okay, then we come to 4. We doesn't see we see try to go to its right, but doesn't have anything right, so we will print 4. Okay, so just a minute. Thank you, Naikach, for your confirmation. Okay, so yeah, so this was about the posterior traversal. Yeah, since we have to go to the left first. So from 1 we go to 2, from 2 we go to 4, 4 we go to 7. We 7 see there are no left and there are no right as well. So we print the value 7 now. Then we go back to 4. Okay, but the algorithm will try to explore the right part of 4, but it doesn't have any right part of 4. So it will print the root that is equal to 4. It will print 4. Now it will go back to 2. But after coming back to 2, it sees that it has a right child. So that is equal to 5. So it will print the 5. That will come back to 2. So now after printing the left and the right, it has the responsibility to print the root. So what it will do, it will print number 2, the node number 2. Then it will go back to 1. Okay, but after going to 1, it will try to explore the right part, which is 3. Again coming back to 3, it will start keep on going to the left part, which will be equal to 6. So it will come and print 6. After that, what will happen, it will go back to 3, because here it has printed the right, and it's time to print the it has printed the left, and it is time to print the right. But 3 doesn't have any right, so it will just print 3, and then it will go back to 1 and print 1. Okay, so this is the post ordered output of the given tree. I hope this part is clear with everyone, the pre-order and the post-order traversal. Okay, so now we will see how exactly we are able to implement these concepts in the form of a code as well. Okay, so this pre-order, post-order, and in-order traversal are extremely popular interview questions, and I would request everyone to kindly note down the concept as well. Okay, so these concepts of pre-order, in-order, and post-order can be implemented recursively as well as iteratively. Okay, okay, and recursively implementation is quite easy, but the iterative implementation is a bit tough. Okay, and mostly in interviews, apart from recursive, iterative is also asked. Okay, both are asked simultaneously. Okay, and it is very important that you know the iterative implementation as well. Okay, so let us look into, yeah. So we discussed about three traversal techniques. The one was in order, pre-order, and the post-order. Apart from that, I also told you that these three are based upon the concept of depth first search. Okay, but depth first search is not enough. Okay, but depth first search is not enough. There is something called a breadth first search also. And if we try to apply the concept of breadth first search while we are doing any kind of traversal in a tree, in that way, what will happen basically is that yeah. So we will be getting a new type of traversal called the level order traversal. Okay. So there is a level order traversal. What happens is that we are given a tree, and this traversal will go explore the tree in level wise fashion. For example, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay, and yeah. Okay, so it will explore this given tree in level wise fashion. So first we got so first we got this tree, the level 1, which is equal to this one. So we will just print 1, then we will print 2 and 3. Okay, so we will print 2 and 3. So after that we will print 4 and 5, we will print 4 and 5, and finally we will print 6. So all these are in a different level. 1 is in a different level, 2 and 3 are in a different level, 4 and 5 are in a different level, and 6 are in a different level. So it printed all the nodes in a level wise fashion. Okay. Okay, so I hope you got the idea. So how do we implement this? We implement the implementation of this concept is very similar to the breadth first search algorithm, in which we use a queue data structure to solve this problem. Okay, so this was about the level order traversal. Okay, so now let us look into a few coding implementations of these traversals. Okay, so what you can do basically, go to the GFG practice portal, and you will find questions related to pre-order, in-order, and post-order traversal. So we will be doing that. Okay, so let's say this is an implementation of yeah. So this is an implementation. The iterative implementation is already written here. So let me comment this part out, and let's discuss the recursive implementation first, and then the iterative we will discuss. Okay, so any idea about how the recursive implementation of pre-order traversal look like? Naikaj? Hello Lalit, hello Naikaj. So anyone? Hmm. Just it's just 3 lines of code, and we will be able to write a recursive implementation of pre-order traversal. So what you can do basically, you can use the idea of depth first search. How do we recursively write for a given tree? So what we can do to traverse the given. So first we have to go to its left, then the root, and then the right. Okay. So that is the how we will implement this concept. Okay. So it's very easy actually. Let me wait a few more minutes if anyone is able to write. Okay. So Vishal has already written. Uh, Vishal is writing root data. First we'll go to data, then we'll go to left, and then we'll go to right. Okay. First root, then first data, then left, and then right. Left node right. Okay. Naika says first we have to go to left, then the node, and then the right. Okay, Vishal. We will not be accessing the data first. We will be accessing the right. First we go to the left. We keep on going to the left, and then after there is no such as left, we print the root, that is a node, and then we go to right. Okay, so this is how the implementation will look like. Okay, so just a minute. Let me just put up the code there. Okay, so let's see. Yeah. So as said by Nikes, first what we will do, we will declare a vector. Okay. So what we are doing here is that we are basically initializing a new function, creating a new function called the pre-order util. Okay, so this is a utility function that will help us print the pre-order traversal. So we are declaring a vector called res in which we will store our pre-order traversal answer. After that, we are calling our utility function called pre-order util, and we are supplying with it the value of root and the result vector. And finally, we will return that result vector. But let us see the implementation of this utility function. It is accepting the root and the result vector. So it is checking whether the root is equal to null or not. So this becomes the base condition of the given value. Okay. So after this is done, then what will happen? It will this is pre-order. Just a minute. Okay, pre-order, it was small error from my side. Pre-order is first root, then it is left, and then it is right. Okay, Vishal, you were correct. Okay, Naika, it should not be left node and then the right. It should be first the node, then the left, and then the right. That is pre-order. Okay, I just confused it with in order. Okay, so another kind of warning and advice here. These pre-order, post-order, in order, you may just forget the order in which it is done. So I would recommend you to kindly memorize it by heart. Okay, so first we will call the null. First we will check whether root is equal to null or not. If it is equal to null, we just return because it will be a base condition. And this will also get executed when we are reaching the leaf node. Because when we are reaching a leaf node and we are trying to call its left and right are basically null. So if it is null, we'll just return. It means that there is no need to do the recursion further. So it means that we will just push back into our data. After that, what we will do, we will just call the left part and then the right part. Okay, because first we have to print the root and then the left and then the right. Okay, so this is how the entire thing about pre-order traversal will work. So let us submit the code and see if it is correct or not. There is a small compilation error. Okay, so I should name this as it is named as current and I am sending root. Okay, so let me name it as root. There is a slight error in naming of the variables. So let us see now. Yes, Naika, sometimes everyone gets confused related to pre-order and in order. Okay, so it's better to develop certain kind of mnemonics that will help you to remember that. Okay, So let's continue. So we are done with pre-order. So let's try to have a look at in-order traversal. Okay, so in-order traversal, let me see if it is present in GFG practice. Yes, it is present. So let me just share the tab then. So this is a tab for the in-order traversal. Okay, and how we will do it? In fact, both the iterative code is also written here, but what I would yeah. So I hope you can see it. Okay, so just comment out the let us just comment out this part. Okay, and let's just say this is a utility function that we have created for printing out the in order traversal. Okay, so in order what happens, we go to the left and then we go to the answer and then we go to the right part. So what I'm doing, I'm declaring a vector called ans. This is a global vector, and then I'm just calling this function in order function. Okay, so in order function which I just created, I will call this function with the root. Okay, and finally I will return answer, because after I call this function, the answer gets filled with the in order traversal. Okay, so let's submit this code and see. So as I just said, first will be the left part, then will be the right part, and then finally will be the first the left part, then the value at the node, the root, and then the right part. So this is the case for in order traversal. Any doubts till here? And any doubts at all? Okay, so in this session we are particularly discussing about the iterative, the recursive code for all kind of traversal. In the next session, or in we will be discussing about iterative solutions. Okay, that is tomorrow. Actually, I plan to teach you more about definitions of height of a binary tree, LC of a lowest common ancestor, and the diameter of a binary tree. So yeah, we will just discuss the definitions there, and we will try to look at the iterative code of this. After tomorrow's session, the next two session and next three sessions, in fact, will be practice session. So we will see live coding implementation of these definitions and topics we have just learned. And in fact, these topics are in itself the questions of an interview. Okay, so I hope everyone will follow me through all those. Okay, so yeah, see, as you can see, all the test cases have passed, so the solution is correct. Now also let us have a look at the post-order traversal as well. Let's look at the Geeks4Geeks portal of post-order traversal. Okay, so yeah, this is a post-order traversal, and I just know, as I told you, the definition of post-order traversal is that first you have to go to the left and then the right and then the root. So left, right, and root. So what we have to do here is that again create a utility function or a recursive function. Okay, so let us just do it here itself. So let's say I declare a vector in TNS, and then again I declare a void. Okay, so first we have to call the left and then the right, and then finally the just a minute, I'm putting up. Okay, yeah. So this is a code. So we have to accept a root of the tree, and then we accept a vector as well in which we are storing our result. So first we'll be checking for the base case. If it is null, we will return, and then we will call the left part recursively. We will call the right part recursively, and finally we will push back our data, the data of the given root in our result vector. Okay. So this part is done. After that, what we will do basically. We don't no longer need this. So we need to declare a answer vector or the vector result. So let's say I write vector int res. Okay, and then what will happen? I have to call my utility function called post order util, and then send my root and my vector in which I want to store. Okay, so and then finally return my list vector as well. So this is the coding implementation for that. First, we call the post order util function, supply the root and the result vector, and then this function upon when it's get called, it will fill my result vector with the post order uh, post order uh, solution of the given binary tree, and then finally I will just return the result. So as you can see that all the test cases have passed, so therefore this question is correct. So let's have any other doubts do you have related to this? We will be discussing about the iterative implementation in our next session. Or yeah, and as I've already told in the beginning of the session, this graph series, tree series, in fact, will continue for the entire month of January. We will be having live sessions every Monday and Tuesday at 10 p.m. It will be a session of around 50 to 1 hour, and the next session will be tomorrow, in which we will discuss about other important definitions, including height of a binary tree, lowest common ancestor of a binary tree, and diameter of a binary tree. So these three are again important. After that, we will be having 2 or 3 practice sessions, and in those practice sessions, we will be looking up into various other questions related related to the topics which we are doing now and we will do tomorrow. Okay, so basically what you can see is that all the sessions will be very very important if you are targeting your internships or placements. Okay, and yeah, so we have moved reached to the very end of our session. Any doubts you guys have, you can write in the chat box. So Naikaj, hello Vishal, are you there? So how did you like today's session? Kindly give your feedback in the comment section. It will be really helpful for me as well. I would be improving in the next session itself. Apart from that, yeah, and one more announcement is that I would request everyone to kindly like the session and subscribe it as well, because we have planned extremely great content on this channel itself. And in fact, what you all can do, and in fact, next week onwards, or in fact this week onwards, we have a dynamic programming series coming up. So graph and trees are already going on, and dynamic programming will be coming up. So basically, graph, trees, and dynamic programming in itself are extremely important topic from interview point of view. So this entire thing will help you prepare best for your interviews as well. Okay. So yeah, this was about the present series, and I would request everyone who all watched me till the very still from the start till the very end to kindly give your feedback about what did you like about this session and how do you want me to improve. Okay. Apart from that, I would request you to kindly check out the description of the streaming itself. You will find a link to the Geeks for Geeks self-paced course, and it is an extremely beneficial course if you are preparing for your interviews. Okay. Thank you, Naikaj. Yeah. So, yeah, with that, let us wrap up today's session. If you do not have any doubt, I'm here for a few more minutes. If you have any doubt, you can write in the chat box. And so, let us see you tomorrow then. Okay. So, all the new joinees who have joined in the last minute, I would request everyone to kindly tune up for tomorrow's session. We will be discussing about height of a binary tree, lowest common ancestor, and diameter of a binary tree. Okay, so every Monday and Tuesday at 10 p.m. on this channel itself, we will be having tree series. Okay, and on this Friday, we will be starting off with our dynamic programming series as well. Okay, so yeah, goodbye to everyone and good night. And in fact, I forgot to wish a very very happy new year to everyone present here. I hope this year brings you a lot of success and positivity, and hope you achieve your goals as well. Okay, keep up the spirit. Yeah, thanks a lot. Bye bye.